All right. We are here with the above average Joe small block Chevrolet build. Because if you haven't figured it out, this is double A Joe, above average Joe. So Joe is working here.
Appreciate
Joe is,
that.
you're welcome.
Yeah.
Joe's been working on this thing for like what, 25 years?
Yeah.
Since you were 10?
I've got at least like a week in just stripping the paint and painting it and crap like that.
Yes, we've
Very
had
meticulous.
yes, we've had to. This is Joe's pride and joy. But we're going to get ready to dyno this thing. We're going to show you the whole build. So hang on. I hope you got your bucket of popcorn because this is a double A Joe build up on a small block Chevy. So watch this because we're going to come back after the build and dyno and try all of Joe's slightly overthinking, trial and error, wants to try this and try that stuff.
It'll be fun.
It'll be fun. All right, let's get at it.
Hi everybody, I'm Joe. This is Steve Morris Engines. You may have seen me in some other videos assembling some engines. That's pretty much what I do here, is build the engines. Today we got a little bit something different. This is my personal small block Chevrolet. I bought complete off of a friend back in Columbus, Ohio. We got a new steel crankshaft, cast steel stroker, 3-inch 750 stroke, 350 main, with the block, obviously, from Perfit. It is internally balanced, so I can put any kind of neutral balance flywheel or flex plate. I have no idea what I'm going to do with this engine, by the way. I don't have a car for it. I just bought it because I thought it'd be fun to go through it and rebuild it. And one thing led to another, and it was, okay, if I'm going to replace this, then I might as well replace that. And you know how that goes.
Spirals into 2 tablefuls of a lot of new parts.
Yeah, I ended up spending way more than intended. But the cool thing about this build, though, is it's not horribly expensive. The whole idea behind this engine is something that the average guy can build and afford. And, you don't need to spend $50,000 to have fun in an old car. And this is going to be naturally aspirated, carbureted, MSD, distributor, just real simple old school stuff. Easy to deal with, easy to tune, not horribly expensive again, very versatile. You can put this engine in anything you want.
What are the power goals you're kind of hoping for?
I don't really know. I think maybe we'll have people guess. We'll talk about what the combination is, and you guys can guess. Yeah, we'll leave it at that.
So what parts do we got here?
So this is our Steel Eagle stroker crankshaft. We've got SCAT 6-inch forged connecting rods, Heath Black hyper-eutectic pistons, not forged but not cast either. So it's a happy medium for the power goals, if we call it that, and the fact that it's normally aspirated, not super high compression. Those should be more than strong enough. The better part is they're very affordable. So that's the other idea here. We're not trying to spend a crazy amount of money. This block is a factory GM block, 4-bolt main from the factory. Ran all the numbers on it. It's a 1984 block, and it's never been milled, the deck surface. And as much as I wanted to mill it, it didn't need it. It is flat, but it does still have the number stamped on it. And everyone knows small block Chevrolets, the second you mill the block, you lose that number. And if you had something that was like a 327 out of a Corvette or something that was rare or numbers matching to the car and you milled that number off, you've almost ruined the block for some people. But I thought it didn't need milled, so no point in doing that and just leaving the numbers on it. It did not actually come in any passenger cars, so I did a little bit of research on the block, and this is a I forget the correct term for it, but it would be like a factory replacement engine from GM. So if you had a car with a 350 in it and it blew up under warranty, then when GM replaced the engine, this is the block that you would get. So the numbers on the block don't actually connect with any kind of model car or, year, make, model of anything. It's just a GM 4-bolt main, 1984 casting, 350 block. That said, using factory main bolts, main caps, I don't think there's anything wrong with that. We are running H series bearings, ACL bearings, mains and rods. It did have a hydraulic roller camshaft in it. I spun it on our cam dyno, and I didn't like it. It was too small. I wanted something a little bit more, so I figured, well, hey, if we've already gone this far, might as well put a camshaft in it, right? Well, if you're gonna put a camshaft in it, you might as well put new lifters in it too. Ron over at Perfect hooked me up with brand new camshaft. This is a hydraulic roller cam, steel core, Morel Black Mamba hydraulic roller lifters. Nice stuff, really, for a street application. It's a billet double roller timing set, 9-way adjustable, so nine keys. So you've got quite a lot of adjustment there, whereas a lot of the cheaper ones just have three keyways in them, or just one. Also got a new oil pump because there was no way I was going to use the old one with how much debris was developed from all of that crankshaft material that is now gone. Pretty much goes over the bottom end. The engine had World Products cast iron heads on it. Decided to reuse those. We worked them a little bit. 5-angle valve job on the intake, a nice radius on the exhaust, opened up the throat a little bit, did a little bit of mild porting to them. Also had to cut the spring seats, and then cut the guides to accept an actual Viton valve seal, where before it had just had like the old school umbrella seal, I believe they call them, or it just kind of hangs out on the valve, and the spring pocket was just machined into the head, and the spring just sat in the pocket directly on the head. I didn't like that, so now it's going to actually accept a spring locator, which is what we got here. So anyway, so stainless valves. These are beehive springs I got from Perfect as well, Engine Pro. Tie retainers. I always really like using beehive springs in a hydraulic roller street engine. They're a lot lighter, a lot less moving weight. The small tie retainer helps too with that as well. And the spring pressure is right where I want it to be. So anyway, we've got a spring locator for our beehive spring, and we've machined the head to accept that. So now it sits in there nice and tight. The spring sits right on top of that. So now the spring is actually riding on a hardened spring seat that's properly locating it. Tie retainers, Engine Pro, new valve locks, because why wouldn't you? I got new rocker arms because this camshaft over here, instead we replaced the camshaft. I didn't want to grind anything special, so this is a shelf cam. It's actually a very common camshaft for a small block Chevrolet for like a lot of just street crate engines. Duration at 50, 230 intake, 236 exhaust, 110 lobe separation. And the one thing that I really didn't like about it is the lobe, well, the lift is 510 on the intake, 520 on the exhaust. I thought those cam numbers sound great, but I want more lift. You know, why only, you know, just over a little bit of half-inch of lift? So the best way to increase lift, or the easiest way and cheapest way, is to, instead of running a 1.5 rocker, which is what pretty standard for small block Chevy stuff, we got a 1.6 rocker. The 1.6 rocker is going to give us 544 intake lift, 555 exhaust lift. Now, I still have the old 1.5 rocker arms, which are comps, and they're actually pretty nice. And I think what we're going to do is try them both. We are going to dyno this when I'm all done with it, and I think we'll run it with the 1.5s first, and maybe we'll put the 1.6 on the exhaust, see what that does, and then run the 1.6s on the intake and exhaust, and just see how much of a difference does that really make.
Yeah, that would be pretty cool.
Yeah, I think so. Hopefully a lot, right?
Hopefully.
Hopefully just
Hopefully a
tons of-
ton.
Anyway, push rods, head bolts, ARP rocker. I got new rocker studs for it, just because I wanted to. Edelbrock, RPM, air gap, intake manifold. Pretty standard stuff there. Velcro head gaskets. Nothing crazy.
Well, sweet. So you're going to start putting this thing together?
Let's get after it. I've already measured the bearing clearances. I've already verified that all that's good and where I want it. And recorded all of that, like I do with every engine. Very, very well documented here. But that's how we just do things here. Every engine we build, very well documented. Like lubing the distributor gear ahead of time, and I like using this stuff. The Extreme Pressure Lube number 3. Pretty much all engine builders on the planet use this stuff. Bolt lube and whatnot. I'm going to install the cam. We've also put new cam bearings in it, obviously. I'm going to install the camshaft first before the crankshaft for a couple reasons. It's a lot easier. Well, I guess maybe 3. One, you can see what you're doing. It's very easy to scratch these bearings. So you want to try as hard as you can to not rub the cam lobes on the bearings like that. So I like putting the cam in first. This is the other reason. I can lube the journals on the camshaft, all 5 of them, because the crankshaft isn't in the way.
Now, do you do this with everything, or?
Yeah. Rather than putting the assembly lube on all the lobes first and then sticking it through all the bearings just like you saw me do, it can wipe off what you've put on the cam, and then you end up with a whole bunch of assembly lube in the front, and it makes a mess.
And nothing in the back.
And then, yeah, not much in the back. So, third reason why we're putting the camshaft in first, or at least before the short block is together. There, spins nice and smooth. Is this is a factory block, so no raised cam tunnel, anything like that. That didn't exist back then. With that said, this is a stroker small block, and the connecting rods will interfere with the camshaft if they're in the same place at the same time, which they never should be when the engine's running. But let's say, for instance, crank rods and pistons were in the block. I would get the cam in, and then eventually at one point a lobe would hit one of the rods. I would have to turn the rotating assembly, get it to clear, move a little bit further, then it would hit the next one, and you can do it. It's just a lot easier to do it like this. So I used to never use assembly grease much before working here, but I actually really like this stuff because it doesn't go anywhere. You know, other assembly lubes, you know, it can eventually, you know, run away. This stuff, you put on the bearing, it's staying there until you start it. Now we can't forget to lube the rear main seal. Any rubber Viton seal, you always have to lubricate, because if you start it dry, you will burn it up. We don't want that. Our crank is installed. We got good in play. A little over 5 thousandths. I'm fine with that. Spins over nice and smooth. We are just trucking along here. You saw the crankshaft is now installed. I set the camshaft in the block first, and I explained why I did that. And rather than moving on to installing rods and pistons, I'm going to degree the camshaft first, and I'll explain why. Partially the same kind of reason why we installed the camshaft before the crank. So that's what we're going to do right now, and I'm going to explain to you why. Okay, it is time to start installing our timing set / degreeing the camshaft. I've already mocked up this camshaft off camera. By the way, this is one of the things I really like about this timing set I got from Perfit. It's a 9-way key adjustable, which is very nice because you can advance and retard the camshaft in increments of 2 degrees, all the way from -8 to +8, which is nice. Anyway, so I found that retarding the camshaft 2 degrees gets it really close to where I want it. So that's where we're going to install it. By the way, if we were going to install this cam straight up like I always do, just to see where it's at to start, and sometimes that's where they want to be. But anyway, you'll see 0 there. So we would line up that keyway on this key, the 0 mark, and we would use this mark here that's labeled 0 to line up with the dot on our cam gear. Now, since we are not doing that, we're going to install it. You can't see it because I painted over it just to make sure I could not mix this up, but that says R2 under the paint. We're going to use that keyway, and you'll see 0, R4 there. This tooth here is labeled R2, so that keyway, using that mark to line up with our dot, is how we're going to retard the camshaft 2 degrees. So, anyway, this gets driven on with a hammer, and yes, it's fine to do it this way. I've had people tell me in the past, oh, you can't beat those on with a hammer, you know, that's hack. Well, even the Jessel drive systems give you an aluminum driver to drive those on with a hammer. So anyway, doesn't hurt anything. That's on. Now I'm gonna get the cam gear kind of close because you can't put the chain on with both gears installed. I'm gonna turn the crank. No rods and pistons in it yet, obviously, so I can easily turn the crank back and forth by hand. And that's our mark to line up with our dot. And if we get the chain right, nope, off a tooth there. We'll slide this over a tooth. Whoops. That's the one. Move the cam a little bit. Line up the dowel. This is another reason why I always delay installing the cam plug too in the back of the block, because you can always push forward on the camshaft. And this is later on, but once we get the the timing cover on and our thrust button in place, and we're setting our camshaft in play, makes it much easier to be able to put an indicator on the back of the camshaft to measure how much the cam's moving back and forth, rather than trying to go through a lifter with an indicator, and it just complicates things. So anyway, real quick, let me just show this before I put this on. So again, nice billet timing set from Perfect. Very excited about it. And it wasn't horribly expensive. Comes with a built-in Torrington bearing on the back, which I love. And I always like to put some assembly lube in there to lube them up so nothing's dry upon first start. And this Torrington bearing just rides right against the block right there. And it's just a much better setup than anything from the factory. Struggle through this again. All right. So we need to draw up these bolts so that our cam gear is mated flush with the front of the camshaft, and our Torrington bearing is riding on the block like I just showed you, just like it would if we were installing it for real. I'm gonna zip these on real quick. By the way, this is my quarter drive impact. This thing, I can literally hold it with my hand. It's not that violent. It sounds really dramatic. There's maybe 15 foot-pound, 10, 15 foot-pounds on those bolts right now. They're just snugged up. Now we got our tool here. This is going to hold our degree wheel and allow us to roll the engine over. To do this, we have to have our number one piston rod installed, or at least mocked up, which is what we're going to do right now. Number one rod and piston mocked up. Okay, got our number one piston and rod mocked up in place. Now we can use our bridge, find top dead center, and set our degree wheel. So we're going to watch this indicator until it stops moving. It was right about there. Zero this out. All right, we'll go back a little bit. All right, coming back up on TDC. Needle stops right there. Okay. Needle stops, zeroed out. We got our timing pointer set already. So now, and yeah, it's just a piece of welding wire. I know that they make the fancy pointers with the clear plastic and the nice line on them and everything. I've used them. They're nice. I get by just fine with this. So anyway, we can pretty much get this out of the way now that we've got our TDC or our timing pointer set. We don't really need that anymore. Now we're more concerned about this gauge here. This is just a dial indicator that mimics a lifter. So this OD here is about the size of the OD of the lifter, and this acts as the roller on the bottom of the lifter, and it's going to more accurately and more easily measure the movement with our cam lobe, rather than just using a lifter and trying to set up an indicator on the lifter. This is just more accurate and, quite honestly, a lot easier too. Pointer set. We're going to start going through the motions here. We're going to keep turning until we get back on the base circle of the cam. Make sure this is pushed down. Zero this out. I think we got a little something on the lobe there, but it's all right. Coming up right off the base circle there. and we're going to stop at 50 thousandths. Almost all cam cards will give you valve events at 50, duration at 50. That's what they're talking about. 50 thousandths off of the base circle of the cam, where the cam lobe's actually really starting to do something. That first bit right off of the base circle is kind of negligent. It's important for some things. Advertised duration. When you see advertised duration, it's always a bigger number. That's going off the base circle to where the lobe actually starts. Duration at 50 numbers, timing events, valve timing events at 50. That's kind of the standard for just degreeing camshafts and talking about that kind of stuff in general. So at 50, we're at 10 degrees of crankshaft position. So what does that mean? That means, generally speaking, at 10 degrees, before top dead center, our intake valve is opening. 50. Okay, so we're at 100 right now. The lobe lift is 340 thousandths. So we're going to go 50 thousandths before, 50 thousandths after. That's how I always do it. So we're going to go, I call it plus, it would be in this case 250 minus 250. We're going to average those two numbers, and that's what's going to accurately give us our intake lobe center line. So we were at 100, we're at 150, that's 200. We're going to stop at 290. And 60.5 degrees there. We're going to go all the way to max lobe lift, which are set up as good because within a thousandth, we're reading 340 total. Now you might ask, why don't we just go to 340 where the needle stops and just see what this says? Hugely inaccurate. You will not get repetitive numbers if you try to degree a camshaft that way. So anyway, so we're coming back to 290 on the other side of the lobe now. We're going to make our pit stop there. Just back to 190 here, 155. Now that's 2, 1, and then back to 50 thousandths again on the other side of the cam lobe. 134 degrees, minus 180 is 46. So I've already gone through this. Yeah, 134, so 46 closed. We had 10 degrees open. So at 50 on the coming up, we had 10 degrees. So intake valve opens at 10, closes at 46. We just saw that. Now, at our plus 290, we had 60.5 degrees. 290 after peak lobe lift, we had 155 degrees crank position. Add those, divide them by 2, average them. We get 107.75 for our intake lobe center line. Was shooting for 108. So that's good. That's as good as it's going to get, because unlike a fully adjustable, let's say this were a Jessel belt drive or something where you can infinitely tune the cam, we can only do it in increments of 2 degrees. But that's good. That gets us really close. If we didn't have that ability, we would only be able to line up the dots and install a camshaft at 0 straight up, and whatever we got is what we got. So there we go. Now, camshaft is now degreed. It's mocked up. We got to install it for real this time. But I'd like to explain something real quick. This is an extremely common camshaft for small block Chevrolets. You will find them all over the place. Freight engines, just regular builds, because it's just a very generic grind that works well with a lot of different combinations. Your average combinations for a pump gas street NA carbureted engine. They kind of got it figured out. So I would have loved to have ground a custom camshaft for this engine, but again, the whole point of this build was keep it simple, keep it relatively inexpensive, and use parts that anybody can buy off the shelf. You can find this camshaft at Jeg, Summit, wherever. They're going to have probably 100 of them on the shelf at least. So anyway, the specs for this camshaft: duration at 50, 230, 236. Lobe separation is 110. The duration numbers, that's pretty close to what I wanted. Maybe a little less on the intake would have been good. A little bit tight separation I would have been cool with, but 110 will work just fine. One thing I don't like about this camshaft is just the lack of lift it has. Only 510 on the intake and 520 on the exhaust, which, isn't, for a street engine, it's all right, but something around 550 or more would have been kind of nice for something like this. So these specs are assuming that you're running a 1.5 ratio rocker arm, which is standard small block Chevrolet stuff. Now, so you can run a 1.6 ratio rocker arm. Everyone makes them for the small block Chevrolet. So what I ended up doing was running this camshaft, and I have a set of Comp 1.5 aluminum roller rocker arms, and I also got a set of Engine Pro aluminum 1.6 ratio rocker arms that are basically the same quality, same style aluminum rocker arm to increase the lift. So with that added rocker ratio, I think we end up with, instead of 510, we got 544, and instead of 520, we got 555. So a little bit better. And I think we're going to play with that on the dyno a little bit and see if it really makes a difference or not. So anyway, back to my point here. Here's what I wanted to talk about. This cam card is very vague, by the way. And by the way, that's the part number. So I think it's an extreme energy comp, whatever. I don't remember what it's called, but regardless, valve timing says here at 50 intake, open 35 degrees, closed 67. If you remember what we just did here to get our intake center line, now our lobe separation is 110. So installing this cam at anywhere between 106 and 108 is perfectly acceptable. So it's not like we're out of bounds here with where we installed this camshaft, but according to the cam card, at 50, it opens at 35 degrees. We're opening at 10. Says closes at 67. We're closing at 46. So, what's going on here? Well, is the camshaft wrong? No, the camshaft is perfectly fine. And to prove it, I ran this camshaft through our cam dyno over there, which basically you can take any camshaft, you stick it in the machine, you set up some parameters, and it will tell you exactly what the camshaft is, which is an extremely useful tool to have. So we look here, lobe separation, it's telling us 110.3. That's pretty close to 110. Now, at 50 thousandths, and it's kind of assuming where I'm installing the camshaft, but it's close. We're at 9.1 degrees opening, 41.38 closed. We got 10 and 46. So we're pretty close. We're within reason. I probably installed this camshaft a little bit differently than what the program is assuming I installed it. What's up with that? We're really close here with our valve events and we just checked the intake center line. It's a 108, completely acceptable for this camshaft. This cam card is incorrect. And what's a little suspicious about it as well is it'll always tell you these specs are for cam installed at intake center line, and it'll tell you, it'll suggest where to install it at, 106, 108, 107, whatever. It says nothing there, which is a little bit weird. The only data it gives you to run off to install this camshaft is, well, install it at 50 with it opening at 35 degrees. If we just did that, we would be crashing valves in the pistons like no tomorrow. And our flow center line would be so far off. I don't even know. We couldn't even do it, actually, with this timing set. To kind of put that into perspective, well, first, so the camshaft that came out of this engine originally that I replaced, that's the cam I replaced this cam with. Lobe separation here is a 106, and it wants the intake valve opening at 1.07 degrees at 50 and closing at 25.31. This camshaft is way smaller than what's in it now. But just to kind of give you an idea, it isn't anywhere near 30 degrees or 35. Another small block camshaft. To kind of put this into perspective a little bit, this is an SMX turbo camshaft right here where I've got it installed at 50, open at 31.5 degrees. Okay, that's an SMX turbo camshaft. Way bigger than this camshaft. Not even in the same ballpark. And it doesn't even open at 35 degrees before top dead center. Close, but you know, completely different camshaft, totally different totally different application. Not even close to the same thing. So I guess the lesson there is you can't always you can't always follow directions, which if you've been watching any of our videos, you've realized that by now. And I don't know what the deal is with that cam card. I don't know if that's a misprint. The fact that it's not filled out entirely is weird. I had a buddy tell me, you know, well, maybe they're talking about at the valve, you know. Well, I don't know why anyone would ever degree a camshaft based on where the valve is at 50 thousandths. You know, we can certainly try it once we get the heads on this thing and just kind of see if it even makes any sense. But regardless, the cam card just doesn't make sense here. But our camshaft is now installed and degreed, and now we just need to take these bolts, torque them up, use our tabs here to lock the bolts in place so they'd never loosen up. Keep on moving. Now, I explained that there was a reason why I wanted to install and degree the camshaft before the rods and pistons. Now, I mentioned when installing the camshaft first, before even installing the crankshaft, that with the extra added stroke here, now this is a standard GM block, so, and this is a standard camshaft, no reduced base circle, and obviously we don't have a raised cam because GM never did that from the factory. So everything's standard small block 350 stuff here. 3-inch 750 stroke is something that Chevrolet never did from the factory. So that's what makes this a 383. GM never had a 383. So with the added stroke, the connecting rods come up and they get close to the cam. They don't hit it, but the cam lobes move out of the way from the connecting rods at the right time. I'd mentioned if I had the rods and pistons installed in the block and then I went to stick the camshaft in, eventually one of the connecting rods are going to hit one of the lobes and I'll have to turn the engine a little bit, push the cam in further, turn engine over, roll the cam, whatever. Just kind of had to jerk around with it just to get the camshaft in the block. Now, once it's degreed and in place, the lobes are always going to swing away from the rods at the right time. So with that said, now that the camshaft's installed, we don't have to worry about hitting the cam with any of the connecting rods when we're putting the rods and pistons in and rolling the engine around. Whereas if the camshaft were just sitting in the block, still not rotating, and we're putting rods and pistons in, turning the engine over, eventually, with the cam sitting still, a rod's going to come up and smack one of the journal or the lobes, and I don't want to do that. Don't want to put a mark in the cam lobe or anything like that. So just a couple reasons there why in this particular case I think it was easier to just go ahead, install and degree the camshaft first, and now we're going to install the rods and piston. First, we got to put our rings back on our number one piston and rod that we used to mock up to degree the camshaft. So, oil expander goes on first. Top oil ring. Now, when I do this, I like to line the gaps up with the skirts of the piston. So top gap for the oil ring, we lined up here. I'm going to put the bottom gap here lined up with that skirt. That puts them 180 degrees apart. The whole goal here is to try to get the gaps of all the piston rings as far away from each other as humanly possible, because when the engine runs, they do rotate, and all you're trying to do is keep them from all aligning and seating in a place where all the ring gaps are lined up on the same plane. Bottom oil ring gap is here. Our second ring goes on, and I'm going to put the gap of the bottom oil rings here. I'm going to put the gap of the second ring right here. And the way you do that, you stick the ring in there like this. This is called the wind method. Wind it around and push in. Push in on the ring and just kind of guide it gently from this side. Keep rolling around, pushing in. Bang, there it is. Flip it around, 180 from that. Top ring gap is going to line up over here. And you make sure you don't put these rings on upside down. They only go one way, so it might be very hard to tell, but there's a chamfer on the top ring. The chamfer always goes up. And the reason for that is when the ring sees compression, the idea is that if it gets around in the groove here, it'll hit that chamfer and force the ring outwards so it seals better against the cylinder wall. So anyway, winding them around again, push in, around, bang, there you go. For people telling me, oh, you got to use, the ring expanders, and you're going to bend the rings and you're going to break them and this and that. And I mean, I've never broken or bent a ring doing it this way. I have used a ring expander before. I'm surprised. I think it's probably easier to bend or break a ring using a ring expander than just doing it this way. That's just my personal preference. So anyway, we're now ready to install our number one rod and piston. Got to put our assembly grease on the bearings. I actually really like this stuff. I've always used the thinner assembly lubes in the past on bearings. Never really liked the grease until I used it, and the reason why I like it, I don't use it on everything, but just bearings specifically, is it doesn't go anywhere. So if you put an engine together and it ends up sitting around for a while, you put this stuff on the bearing, it's gonna still be on the bearing months later. There's no chance it's just gonna run out, drip down into the oil pan. And that right there is just fine. I know there's a lot of builders that you know, will oil down the cylinder walls, and then they like to squirt oil on the rings and everything too. And you know, that's all fine. I actually used to do it that way, um, but anymore I just lube up the cylinder wall and just push it in. The rings grab it. I haven't had any issues. Haven't seen any kind of scoring the cylinder walls or anything like that. Doing it that way. So we'll put our crank around bottom dead center there. Small block, big block Chevrolets, even Mopars. The tangs for the bearings always face outside the block. Another way that you can make sure you're doing this right is the chamfer on the rod has to line up with the fillet on the crankshaft. So the first connecting rod, the front of it always has the chamfer on it. Number 2 is going to have the chamfer on the back side of it. You'll know soon if you got it in wrong. Now, being a small block Chevrolet, it's also important a lot of times, not really in this case because both the valve relief pockets are the same size, but a lot of times you'll have one larger and one smaller. Obviously, the larger ones for the intake, smaller ones for the exhaust, and not all the pistons are identical. So you'll have to make sure that you put the pistons in the right order. You know, small block Chevrolet, you got exhaust valve, intake, intake, exhaust, exhaust, intake, intake, exhaust. Unlike an LS engine, where intake, exhaust, intake, exhaust, intake, exhaust, and so on. So we install our ring compressor. This is a one-piece ring compressor. These are very nice. They're tapered inside. Make the chances of a ring popping out and breaking or bending a ring very slim. So I usually do this on a bench, so it's kind of hard to do it like this, but kind of visually make sure our rings are all where we want them. This is your last chance right now. Yep, you all look good. Pull our ring compressor up here. Make sure our rod orientation's correct. Valve reliefs are in the right spot, facing inward. Front of piston, front of rod. In we go. Use a long screwdriver and lay it on the rod journal here and through the rod bolt hole to basically hold the connecting rod up, and then I'll drive the rod and piston in. Take a quick look, make sure it's still aligned. Looks pretty good. Rings are through in the bore. Hold the screwdriver up so we're not rubbing it on the journal. We'll get it close. Now I can hold this end of the rod, and I can also push this end of the rod against the crankshaft and straighten it so that we don't drive the rod into the journal crooked. And we are now seated. We take our rod cap. Already lubed up the bolts, bearings, everything like that. Tangs are all facing out. You want to snug these rod bolts up evenly so these dowels and the rods don't get upset, you know. Get those snugged up. And these rod bolts go to 43 foot-pounds. They're just a 3/8 bolt. And we're going to torque it in one smooth, singular motion. No step torquing like you would with head bolts or main studs or anything like that. Just one smooth pull straight to torque. Boom. Check them again. 43 pounds. Good to go. Don't want to step torque these bolts. You can create what's called shank twist, and basically that means that the shank of the bolt will twist slightly and fool your torque wrench and make you think that you're torquing them up to a number that you really actually aren't in reality. So just got to do that 7 more times. A lot of people like to turn the engine 90 degrees and install the rods and pistons vertically straight down, which is completely fine. I've even done it that way in the past. I like to do it this way because I can see what's going on. I can drive the piston in this way. I can watch the rod, make sure the rod's, not crooked. Then once it's seated, you can put the cap on and you can torque it right there in place. Whereas, the block's vertical like that, nothing wrong with this, but you install it this way, knock the piston down in, then you come in from underneath, tighten up your rod bolts down here. You either snug them up, do all of them, roll the engine upside down, and then torque them later, or you just keep flipping the block upside down, torquing them, flipping it, and going back and forth. I find it easier just to do it like this. So and excuse my engine stand, it's not the fancy crank ones, so it's just a cheap whatever stand. But anyway, that's why I assemble engines this way. I've gotten a lot of questions about that in the past, so just figured worth mentioning. Okay, so our rods and pistons are installed now. While I was upside down, went over all the rod bolts, just checked them, make sure they were all torqued, even though I knew they were all good. Got the oil pump pickup on, oil filter adapter, that kind of stuff. You just do it while the engine's upside down. So our basic short block is done. I was just about to install the front timing cover, and which incorporates a roller thrust button, and there's a little bit of screwing around with that you got to do to get, because that is what controls the end play of the camshaft. So right now I showed you how the timing set has that Torrington bearing on the back side of it that rides against the block. That keeps the camshaft from going any further backwards. But there's nothing keeping the camshaft from rolling forwards. Now, this being a hydraulic camshaft, I'm sorry, a hydraulic roller camshaft, there's no resultant force on the camshaft that's forcing it backwards all the time. It's kind of floating in there. So you got to have that thrust button, and you got to have adequate end play to let the camshaft kind of float in there, not bind up. But obviously you don't want it rolling back and forth way too much. With nothing in there, you can see just how much the whole camshaft can slide forward and back just with the chain. The chain's the only thing stopping it from coming all the way out. So anyway, I was getting to that point and realized we've been building so many small block Chevys here this past week that every last one of our front cover gaskets I had on the shelf are missing. We used them all up. So gotta wait till tomorrow to get those gaskets. It's kind of annoying, but no big deal. So we're gonna move on to cylinder heads. And here's what I got. These are what came on the engine when I got it complete. These are World Products Sportsman 2 200cc intake runner, 72cc chamber. I actually CC'd them. They're more like 71, but I was just checking them because we did deck the heads. And the machine, I unfortunately don't believe I got that on film either. But anyway, so we decked the heads, cleaned them up. I did valve job to them. Really opened up the throat here quite a bit, and got a really nice valve seat on it. Valve seat pattern rather. Lap the valves in. The valve job looks beautiful. Super happy with it. But on top of doing the valve job, opening up the throat a little bit, kind of help with some flow, Did a little bit of just some minor porting here. Mainly was just kind of focused on the entryway into the port. There's a major choke point here with pretty much all small block Chevrolets, even big block Mopars. They're very similar. They have the same problem where push rod gets really close to the intake runner, and the intake runner has to kind of curve in to clear the push rod, but they do leave quite a bit of material there. So I was able to take a little bit of material out there and a little bit here too as well on both sides, just to kind of open up that choke point there. That's mainly all I was really concerned about doing. I could have spent days doing a full port on these things only to make them maybe just a tiny bit better. I think between the valve job, opening up the throat, and just kind of doing this, also gasket matched, or port matched rather, the ports here to the intake manifold, which is drying. So anyway, that as far as the heads go, also cut down the guides, the OD of the guides, and cut out the spring seats, because the way the heads were assembled before, the valve spring was just sitting directly on top of the cast iron, and there was a small pocket there that the valve spring kind of fit in, which, I mean, I guess is probably okay if you have really low spring pressure and a really calm cam, probably get away with that. I didn't like that at all, so I machined down the guides. So now we have a hard ID locator for our spring that fits in there real nice. So now the valve springs have a nice hard seat to sit on, and they're located by the seat, by the inside of the valve spring itself. Now that leads us to our valve spring. Beehive Spring Engine Pro from Perfect. This is my favorite design of valve spring for this kind of application. You pair this with a tie retainer, which I also got, which I really didn't need to do, but one of those things kind of get a little bit out of control here. Might as well do this, might as well do that. As opposed to, let me find an old spring for comparison. This is actually a much weaker spring than this right here, but this is your traditional spring. You notice it's the same diameter top to bottom. If you look at the Beehive, you'll notice it's wider at the bottom and it gets smaller and smaller and smaller towards the top. Now, there's a couple advantages here for that. You know, when you talk about Valvetrain weight, when you factor in the spring, typically it kind of averages out to where you just take the weight of the spring, cut it in half, and that's the moving weight. Even though all the coils are technically moving except the bottom one, the top coil's moving the most, and, you know, progressively gets less as you get down the spring. Typically, when you talk about Valvetrain moving weight, you use about half the weight of the spring. Now, the Beehive spring, as the coils get closer towards the top, it's actually lighter on this half of the spring. So the moving weight is actually less with a Beehive spring, just from its design naturally. The other advantage is as it winds smaller and smaller towards the top, it allows you to run a smaller retainer, which weighs even less. Now, if you pair that with a titanium retainer, this retainer weighs like almost nothing. It feels like it would almost float away. So I did do a little bit of math, measured all the springs, steel retainers, you know, using the standard style kind of spring versus this. And basically what I concluded was, if you use this spring with a tie retainer versus a spring like this with a steel retainer, the moving Valvetrain weight savings across all the valves would be about the equivalent of using titanium intake valves. That doesn't really translate to anything meaningful. It's just kind of interesting. But what it does mean is that our Valvetrain moving weight is decreased by using this style spring. And on top of that, this spring for a hydraulic roller setup, you don't really need a ton of spring pressure anyway, and this offers just as much spring pressure that you would in a traditional style spring. So you're not sacrificing spring pressure, spring rate, anything like that in this application, where the demand for spring pressure on the seat and at full lift is much less than it would be if you were in a solid roller race only situation. Our valves are not titanium, sadly. They are just generic stainless valves, which is fine. Intake and exhaust. You can see how nice our locator fits on the spring. We're going to be using Viton valve stem seals on all 16 valves. Another thing I had to do with these heads was machine down the very top of the guide and trim them down and put a chamfer on them to fit these seals. These heads were using like the really old school umbrella style valve stem seals that like they used back in the 70s. These seals are way better. And by the way, this isn't a seal. This isn't sealing the stem of the valve. It's metering how much oil is allowed to get through. Now, this is for a street engine application. And a lot of race engines, they don't run valve stem seals at all because the more oil, the better. And if they smoke a little bit, who cares? It's a race car. For a street engine like this, you need to run a valve stem seal because it's too much oil will get through the guide into the chamber and burn up, and you'll see smoke out the exhaust, and nobody wants that in a street car. So this will meter just the right amount of oil to get through to lubricate the valve stem and keep things working great without excessively oiling the valve to the point where we're burning oil in the chamber. While we're here, closer look at the heads. They are real products, Sportsman 2. These are all of our Valvetrain parts. I just went ahead and got new everything, even new keepers. These are our 1/6 rocker arms that I was talking about earlier. I have a full set of comp 1/5 ratio rocker arms. So we're going to be using both. As you can see, they're pretty similar. They're both aluminum, roller tip. Nothing super crazy special there. 5/16 push rods because we can get away with it with our spring pressure. Just traditional guide plates. Those are our head bolts. And I went ahead and got new, longer ARP rocker studs. I like to run a longer rocker stud. If Perfect had a longer one in stock, I would have gotten an even longer one. Stud rocker arm. You don't want the rocker arm to be riding the trunnion of the rocker arm here. I know this is really hard to see. To be riding right up on top of the threads here. As a matter of fact, I would rather them be all the way down on the shank, but I got a taller stud so that the rocker arm trunnion sits lower on the stud itself, and we have more thread engagement with the poly lock. Not too much thread engagement to where the adjuster screw on the poly lock is gonna stick up super far. You don't, if you're rolling around with your valves adjusted like that ain't good. So too long is also a problem. Anyway, so that pretty much covers it for top end stuff. The intake manifold is it's a 4150 style Edelbrock air gap, former air gap, what you see on almost every small pluck Chevrolet out there anymore. That's a street engine. So I think next, since we got a pause on the engine, the short block, we'll go ahead and assemble the cylinder heads. I guess before we do that, Let's talk about the valve springs and the pressures. So hydraulic roller cam, 544 thousandths of lift on the intake, 555 thousandths on the exhaust. That's assuming we run the 1.6 rocker arms, which I'm pretty sure we're going to. So on the seat, so seat pressure is what we call it. Got about 160 pounds, which is pretty good. It doesn't really need any more than that. And then open, we've got about 335 pounds open, which is plenty. It should be just fine to run to as much RPM as it's going to need. I can't imagine it's going to need. If it gets to 6,500 RPM, that's probably as much as it's ever really going to need to spin. I don't see this working. If it makes power at 7,000 RPM, I'd be blown away. If it peaks around 6 to 6,500, that's kind of what I would expect. If it carries it out to 7,000, that'd be cool too. But anyway, we'll see. But regardless, our beehive spring package, along with the tire retainers and everything, this whole thing should work really, really well for what we're doing, or what we're trying to do here. So, all right, let's put these heads together. And real quick, before we assemble these, I've already done it, but just to show you, we need to verify what our install heights are and set them. So basically, our install height is with the retainer installed, what is the distance from the spring locator to the bottom of the retainer? In other words, how much are we compressing this spring with the valve being closed to get to our seated force, which we just went over. So we know that our number, the target is about 1 inch 720, and we're going to use this tool here to measure exactly what it is that we have. For our keepers and retainer in place, just like we would if we were installing it with a spring, we're going to turn this down until it tightens up. And we've got right about 1 inch 720. Then a couple thousandths. So our exhaust, we'll check our intake. Again, I've already gone through all of these and set all of them. So let's verify again. 1 inch 720. So there you go. 1 inch 7 and 20. So basically how this tool works is you've got a scale. And you can see, maybe. So you see that 6 and that line there. If we line up 0 right there with that vertical line, that'd be 1 inch 600 or 1.6 inches. That would be 1.610, 1.615, 1.620, so on and so forth. Then you got 7, 1.7 on the dot. 1.710, 15, 20 is where we had them set. Keep going. You expose the 8. Same deal there. So on and so forth. And some of these, I don't believe. Oh yeah, this one goes up to 1,200. It's not uncommon and higher horsepower stuff to install them, you know, with all much higher lift camshafts, with much heavier duty springs. You just simply need more install height just to fit the spring and the amount of lift. We're dealing with a little bit over 1/2 inch of lift here. We don't need that much. We don't need that much room to play with here. Isn't it funny how something as simple as a paper gasket can completely stop an engine build in its tracks? happens more than you might think. Anyway, we are back here with the average Joe, the above average Joe small block Chevrolet. We had the pause on it because we didn't have gaskets for our front cover, and we still need the set camshaft end plate. So we moved on and we put the heads together. So we're back to this. Kind of a little bit of an interesting timing cover. It appears to just be a factory sheet metal small block Chevy cover like you would see on anything else. But it is a two-piece deal. I've actually never seen one of these before. I'm sure they're pretty common. We usually just use the billet Chloe's cover with the removable thing here with the roller button in it. It's adjustable and it makes it very easy and it looks nice and is what it is. This is what I got. This is what we're going to use. So let's go through it real quick. All right, here we are. Time to install the front cover and set our camshaft end plate. This two-piece front cover deal, this part goes on first. It's already got this area here to accept the oil pan gasket and goes on just like that. Now we'll have to seal this to the block, and then our cover goes on top of that, which we will also have to seal our cover to this plate thing. This goes on here. The cover goes over the dowels just like any other cover would. And then there's 3 studs down here at the bottom that take these little nuts, and that's how you get the bottom part right here to bolt up here and seal it all together, or else you have a massive oil leak down here, which is no good. So I think what we're going to do, I'm not really sure exactly where we are going to be with this. I do have a rollerize thrust button, and that goes right there. So as the cam rolls forward, the thrust button is going to use the front cover as a stop. It's not the best way to do it, but it works just fine, especially dealing with a sheet metal front cover like this. But it's going to work just fine. The alternative is a lot of aftermarket blocks. All the dark blocks, pretty much everybody's aftermarket block, has a provision where you have a couple drilled and tapped holes in the block and a thrust plate that goes on over the camshaft, and that actually keeps the camshaft moving forward, and your thrust and everything is set with the timing set, and you don't have to deal with any kind of thrust button or any of this kind of crap. It's already set, and you just bolt whatever cover you want on, and you're all good to go. This is a factory block, so we don't get that luxury, so we're going to use the thrust button. But it is a rollerize thrust button, which is much better than, you know, just the regular plastic ones that just kind of ride in there. So what I'm gonna try first is, I thought about, let me explain this really quick. The whole purpose, because you're probably asking, why is there an extra piece here? Why not just bolt this straight onto the block? Which is what you would normally do. The whole point of this is so that you can put this piece on, and then the front cover is now removable because this bottom part I just explained that holds the oil pan gasket is no longer attached to the front cover. So normally if you had to remove the front cover, you would have to drop the oil pan down and break the seal there and then pull the cover off if you needed to get to the camshaft or the timing set or whatever for any reason. The point of this is that you can have this on, the pan on, and you can remove this with the pan still sealed all the way across the bottom of the block here. You don't even have to worry about it. So that's kind of nice. It's you know, it looks factory, but it is removable. So what I thought about doing, I haven't made up my mind yet, was maybe gluing this, you know, with RTV directly to the block, and then using a gasket here and maybe leaving the gasket dry or dry on one side, so that this can be taken on and off without ripping gaskets apart. Because I don't see any reason why this would ever need to be removed after the engine's complete. But if you ever did, it would, the last thing you'd want to do is pull this off and then separate this from the block, breaking this seal while you already got the oil pan bolted in place, because you're going to have a nightmare of a time getting this to seal back up. So the whole point would be get this glued so that it doesn't separate. So if you do pull the cover off, the cover comes off, this stays in place, this stays sealed up against the block, and you can take this on and off as many times as you want. Whoops. And no problems. That's the goal. So what I'm going to do is try using 2 gaskets. Each one of these gaskets, well, let's see, I think they're like 20 or 30 thousandths thick, something like that. 28 thousandths, so about 30 thousandths thick. So, you know, using 2 gaskets is going to affect the end play of the camshaft, because we are moving the cover out another 30 thousandths if we use 2 gaskets, which looks like we may or may not have to do. But I'm going to mock this up dry. Whoops. Slide that on. Then we'll put our second gasket on. And again, we may or may not use both these gaskets. We'll see. This is a little bit tricky to do, actually. All right, hold on. Rewind. Let's get back on the dowels here. Okay. I painted all these parts separate, by the way. I stripped everything down to bare steel, everything, block, all these parts, painted everything individually so it looks super nice and killer, and then ended up scratching and chipping everything anyway, so it's going to have to be touched up after we're done. Anyway, we'll snug this cover on and just see where we're at and give us an idea. I do have 2 more that share the bracket for the timing pointer. As a matter of fact, it's this one. Move this one down here. Timing pointer. Snug all these up. What we're going to need to do is set up an indicator. I mentioned earlier I would leave the cam plug out in the back for this specific reason. Unfortunately, this is my personal kind of crappy engine stand, and there's a lot less room back here for an indicator. So let me figure that out really quick, and we'll see what our end play is. I'm gonna have to use a different kind of indicator to get back there. We could try to, no, that's not really gonna work. So let me figure that out real quick. All right, so I just very quietly borrowed an indicator from Brock while he's not here. We have a ton of end play here. Let's see. Let's go back here. Yeah, it's even, that'd be 20, 40, 50, and it's even, it's so far out, it's even going beyond where the indicator's at. Okay, we've got way too much. So I do have a 30 thousandths thick spacer we can put in. We can try that, and we might have to do away with one of these 2 gaskets also. we'll see. So let's bust this back apart again. Add our spacer. Let's play this game again. There's a 30,000 spacer there. It actually fits in there perfect. And I might be okay with doing away with one of these gaskets. This is kind of a pain in the butt. 2 gaskets, 30,000 spacer. What do we got now? So we are on the indicator the whole time now. I'll try to do this slow. It's 20, 40. Ooh. All right. It's at 50. We could take a gasket out. That'd buy us 30. So clearly we need to tighten this up. So we're either going to add more shim behind the thrust button or remove one of these gaskets, or possibly a little bit of both. Let me see what we got here as far as shims go, and we'll figure it out from there. So more shim behind the thrust button, 2 gaskets. I think it's probably best to use both of them. Like I said, I think we'll just glue one and then leave one unglued. But we've got, that's all the way back against the Torrington bearing. Relaxed, I'm not pushing on it or anything. That's all the way forward, relaxed, not pushing on it on the front cover. So we got like 4, like maybe 5, probably more like 4,000s. I'm actually perfectly okay with that. Because as you can see, if I push forward on it, those sheet metal front covers, even the Chloe's ones, the fancy ones I was talking about earlier, they flex probably just as much as these do. So anyway, my point is that they flex. So, you know, we've got, without any pressure on either the Torrington bearing on the cam or the roller thrust button, we've got, you know, a solid 4, maybe 5. I'm totally okay with that. We're gonna leave that alone. It should have no problem. I don't like having an excessive amount of end play in the camshaft. It just doesn't need to be there. A, and B, if you're running a distributor, every time the camshaft moves this way or that way, it slightly changes the ignition timing. It turns the distributor gear a little bit one way or the other. So minimizing that, I think, in my opinion, is always a good thing. So that's going to be the setup. So back to the front cover. I think we will go ahead and I take this back off again. Glue the front gasket, both sides, to the block and to this first plate, and then leave the second gasket, maybe glue the second gasket to the plate and then leave the other side dry. Here's the thing, we're gonna dyno this engine, so worst case scenario, it leaks. If it leaks from the front cover, I'll know why. And because of this whole setup, it'll be a quick, easy fix, because all I gotta do is pull off the front cover and you don't have to worry about the oil pan or anything like that. So I think that's what we'll do. Yeah, see, that's the thing, because these studs at the bottom, it wants to pull the whole thing apart with the cover, and I want this first part to stay on the block. We'll glue both sides of this gasket get this glued to the block so it never moves. And then this gasket we'll just put on dry. Well, let's see here. I actually can't do that because I gotta seal it down here too. So that basically means I have to put some sort of sealant, some sort of RTV across the bottom to seal the bottom portion here. Because this whole piece right here just sits flush against this piece. If there's nothing, no gasket there or anything, then that's gonna leak like crazy. So, but if the oil pan's in place, the oil pan's gonna be holding this. So even if I have to pry on the cover to separate the RTV here at the bottom, it should just come right free. The only other thing would be is just trying not to pull the top part of this out and unseal it. So I think that'll work. Yeah, we'll just we'll glue this, both sides of that gasket to the block, and then we'll just glue this portion down here at the bottom, and we'll leave the rest of the gasket dry. And when it comes time that when we got to take this cover off, the oil pan will be holding it down here. We can break the seal at the bottom there and hopefully just slide it right off without pulling anything else off. Shouldn't if there's no glue between here and there. So, yep, that's what we're gonna do. All right, front covers on final. We're good. Everything's glued from that backing plate to the block, and then RTV across the bottom between the front cover and the backing plate, and then the back side of the gasket between the cover and the backing plate. The back side of it is RTV, the front side is dry. So should be able to remove this without upsetting any of the other stuff. All right, so we got our balancer on, and now we need to set our top dead center marker or timing pointer here, or just our pointer rather. And the way we do that is kind of back to where what we did when we degreed the camshaft. So got our timing pointer here, two little screws here. Now you can slide this back and forth. Now all we have to do is rotate the engine till we're watching that indicator on number 1 again. Ooh, just a little bit fast. Right there. TDC. Now, you can see our top dead center marker there on the balancer. Kind of want to go through this really quick. So, engine's at TDC. There's our marker. Now, we can slide the marker back and forth. Okay, let's say we set it right there. Looks like it's dead nuts on top dead center. If you look at it this way, gee, it's half a degree off advanced. Oh, it's half a degree off retarded. That's called parallax error. The good thing about these pointers is they stay very close to the balancer. So the closer it is to the balancer, the more accurate it's going to be, the less of a parallax error you can get looking at it back and forth. So what I like to do is set these up so if you line it up to where you're looking at the center line of the crank bolt, that should be your perspective looking at the pointer. You know, pretty much right on there now. It seems really simple, but it's actually pretty critical, especially for this engine right here, because it is going to be carbureted with old school traditional style distributor. So it's critical that our timing pointer is accurate because that's what we're going to use. I just moved it to set the ignition timing with the timing light. There's no cam sync or cam sensor or nothing like that with this engine. It's you turn the distributor until and watch the timing light until your ignition timing is where you want it. You know, there's times where I've dealt with used cars, used engines, something somebody else did however many years ago, trying to set the timing, and a lot of times the timing pointer isn't right. So you could be sitting there with a timing light trying to get the run good, and you're like, well, what the heck? You know, the numbers all look good and this thing still runs like crap. Well, it could be the timing pointer's not even correct. So when I do this, I always Loctite these screws in place so it can't move. And sometimes I'll even go as far as filling up these grooves with silicone so that somebody else can't move it. Because right now, this is as accurate as it's going to get with an indicator on top the number one piston, TDC, this marked. There is no better way to do it. Once the cylinder heads are on, you know, there's ways you can get close, running a piston stop through the spark plug, rolling one way, going back, rolling the other way. You can also take the intake valve spring off, let the intake valve drop down, put an indicator on the intake valve and rotate the engine around and watch the intake. But this is the most accurate way to get this set. And we are dead nuts on right now. So when this thing's running, we got the timing light on this pointer here. We're going to know exactly what the timing is at. No discrepancies there. And with this nice pointer, we shouldn't have a parallax error either. You know, even just looking at it right now, it's pretty difficult to try to look at it wrong, you know. So closer the better. I've seen some pointers where they're half an inch away from the balancer, and it's like, okay, I mean, if I slightly move my viewpoint this way, it could change 3 degrees, or vice versa. So that's it, we're good there. I rechecked our end play on the back of the camshaft there. We're still at 4 to 5 thousandths, and now it's time to roll this thing over and put the oil pan on and seal this thing up for good. All right, now this is what I call a complete short block. Everything, head gaskets down to the pan, done, ready to go. The hypereutectic pistons are would be the weak spot if there was one in this short block. I probably wouldn't run these pistons. I'd start to question them over maybe like 500 horsepower. I don't think this is going to make that much. I'd be kind of surprised if it did, but I think it's well within what we're going to be doing with this. NA, pump gas, low compression. This thing's just under 10-to-1 compression. It should be fine. The crank and rods are probably stronger than the pistons are, but the hypereutectic pistons, they're a happy medium. They're definitely stronger than a cast piston. They're not as strong as a forged piston, but they don't expand like a forged piston does. So you can run tighter piston to wall clearances with a hypereutectic piston because it grows about just like a cast piston would. So for street use, and if you were to daily drive this, it might actually be a better option to run the hypereutectic piston because it acts like a cast piston, but it's stronger than one. It's more brittle than a forged piston. A forged piston's always going to be stronger, but forged pistons also do expand a lot more. So you have to have extra piston to wall clearance. We make the bores a little bit bigger with basically every engine we build here has forged pistons in it, but we'll have extra clearance in the cylinders for those. And if you were really concerned about it, you might hear a little bit of piston rocking, so to speak, when it's starting up cold. that quickly goes away because the pistons heat up pretty quick. That's a forged piston. You're not going to have that with a cast piston or a hypereutectic because the piston in the wall is already much tighter, actually quite a lot tighter. Now, speaking of heat, we got Engine Pro rings in this thing. You have to, if you're running a hypereutectic piston, you have to gap the rings, at least the top ring, about how you would if you were running a forged piston. Second ring, not so much. So the ring gap is opened up quite a bit on the top ring. I say quite a bit in comparison to if this were just had cast pistons in it, we would probably get away with 15 to 18 thousandths of ring gap. We got like 24, 25, I think. I got it written down on the top ring and a little bit less than that on the second ring. The reason for that is a hypereutectic piston will heat up the top ring a lot more than a cast or forged, well, more than a cast piston would. So because of that extra heat in the ring, you got to account for that expansion rate of because the rings themselves, when you got to think about, they get hot, they grow too. When they grow, the gap gets tighter, gets closer together. It's exactly why you run more end gap with higher levels of boost, higher power levels. If you're running a lot of nitrous, all these things you think about, you take into consideration when gapping rings. Obviously, the more boost, the more nitrous, the more power, the more cylinder pressure, the more heat, the more end gap you have to give those rings, which could result in just a minor bit of blow by when the engine's cold and not in the boost. But the important part is when the engine's being used for what it's intended for, like any race engine, wide open throttle, screaming down the track, you got to make sure that you got enough end gap to where it's safe, because that's where the engine's going to be used. This is safe in all situations. Fired up cold in your driveway, you want to drive this thing every day, like I said, go for it. That's kind of how I'm building this thing. It's just the ultimate street engine. If you want to go to the track and have fun for a day, making passes, it's going to be safe for that too. That's the whole idea of just an all-around great strip street. I almost said drag and drive. Strip street engine that you could daily drive and is reliable and fun and doesn't cost a fortune. That's where we're at. So we are actually at a point now where we can put the lifters in and we can actually bolt the cylinder heads on, which is what we are going to do next. Beyond that, Valvetrain, rocker arms, push rods, setting the preload and dropping the intake manifold on this thing. Beyond that, snapping the distributor in, setting that up, carburetor, everything's super simple. No EFI here. So we're actually getting pretty close. All right, let's slide these lifters in here. Always like to soak hydraulic roller lifters before installing them. These are Morel Black Mamba hydraulic roller lifters. Also got these from Perfect. These are really, really good hydraulic roller lifters, honestly. For just a street strip application, I don't know if it gets much better than that. Maybe Johnson's got something good, but these are outstanding lifters. We use them all the time in all sorts of applications. Just like everything else that I've got from Perfect for this engine, I've replaced everything. I mean, everything is new. If it was in stock at Perfect, chances are it's in stock at Jegs and Summit. So this is all easily obtainable stuff anybody can get. As far as the tie bar goes, as long as you can read Morel and it's not upside down, you're okay. I don't know if it's as critical with parallel lifters like this, like in a small block Chevrolet, but definitely in something like a big block Chevrolet, it is absolutely critical that you don't have the tie bar upside down, so to speak. There's always an arrow, almost always an arrow, pointing up if it doesn't have a brand name on it, to make sure that you've got them oriented right. Because Big Block Chevrolet, some other engines, the lifters are actually offset. So if you were to install them like this, where Morel is now upside down, the lifters are turned at an angle against the camshaft, which will almost immediately destroy the camshaft and lifters and force you to entirely rebuild. Probably got a decent amount of oil in the pan already. All right, prep our head bolts, and let's bolt on these cylinder heads. Okay, forgot to mention, before we install these cylinder heads for real, we need to check a couple things, just verify it. One being piston to valve clearance. And while we're doing that, we're also going to check our rocker arm geometry, which I've already done that, but we're going to go through it real quick. You never wait to get this far along to then check your push rod geometry, or your rocker arm geometry, sorry. You mock it up ahead of time and make sure if there's any adjustments you got to make, you make them before you got the entire short block ready to go. So you notice we got test springs. This is cylinder 1. Test springs on our intake and exhaust. We'll drop our push rods in, and the engine's still at TDC, so we should be on the base circle, but it doesn't really matter because we got test springs on. So we're gonna run the valves to their motions here, and I'm pretty confident that we're going to have so much piston to valve clearance that we're not even going to have to get the indicator out. But we are on the base circle of the cam on the intake and exhaust, so we might as well mark where our rocker arm's at. Now, if you notice, I marked, I drew the stem tip of the valve with just a couple Sharpies. It seems to work just fine. And what I'm doing here is I'm just rolling the roller on the rocker arm just to leave a better mark. Sometimes it just won't leave a mark at all. So anyway, I gotta move this a little bit, but okay, so let's go through the motions here. Exhaust starting to open. As it's opening, I'm going to keep rolling the roller. Now, this is just visually kind of checking, and the only way to adjust this with a pedestal style rocker arm like this is with the length of the push rod. So these are non-adjustable rocker arms, obviously, so all of your adjustment is coming from the push rod itself, and the rocker arm just floats really on the rocker stud. The valve and the push rod are keeping the rocker arm suspended against the polylock. But anyway, intake starting to open. Now I can actually roll the roller because we have test springs. If we did not have the test springs on, there's no way you're going to roll that roller just with your finger. There'll be too much pressure against the rocker arm. So no preload or anything set. You can't, because there's not enough spring pressure on these test springs. So I just kind of set them to there was zero lash. But you can kind of get the idea there. And watching it go through the motions, it kind of starts a little bit outside. It sweeps its way in towards the center, which is good because the further the valve opens, the higher the spring pressure is getting. But one thing I really like about this is if we average this here, yeah, we've got maybe like 65, 70 thousandths of spread. Actually, yeah, maybe a little less than that, maybe like 65 thousandths of spread there, from where the roller position starts to where it swings and then it comes back. That's actually pretty good. I wanted to make this perfect. We could move it in just a little bit, but I actually really like where it's at right now because at max lift, it's right in the center and it stays in the center throughout most of the travel, and then slowly kind of walks outside towards closing. Could make the push rod slightly shorter, and that would bring things in, but it might also open up the sweep, so to speak. You know, our sweep's about 65 thousandths now. We could move it more towards the center, but then end up with a larger sweep. So I'm pretty happy with where it's at right there. Again, like I said, that's just the visual way of checking it. You know, the actual way, and Steve's got a video on it, but the best way to check it is at half lift. You look at the rocker arm where it's at. You want the roller to be in the center of the valve stem tip at half lift, and then minimize the sweep. And there's plenty of videos out there on that explaining that whole concept and that way of checking. But I am perfectly confident that this is going to be just fine. No abnormal wear, no broken parts, no nothing. So let's get back to why we set this up in the first place, and that is to check piston to valve clearance. And like I said, I'm pretty confident it's going to be a lot. Sauce valve it's opening, piston's coming up. We got miles there. Miles there. And piston's coming up as this valve is closing right now. So the piston is chasing the valve right now. Miles. Not even worth noting on the exhaust side because there's so much. Now the intake valve is starting to open. Got a ton there. So now the intake valve is now chasing the piston because now the piston's going down and the intake valve is opening, and it's trying to open as fast as it can as the piston goes down. But I'm turning this thing maybe 5 degrees at a time. At no point are we even anywhere near the piston. Now, if we were opening the intake valve 35 degrees for top dead center, like the cam card said, which might be a different story. Maybe not. I don't know. You know, some of these really high horsepower setups, small block Chevrolet, I'm sure they got that intake valve open pretty soon. But anyway, that's a quick and dirty rundown on just verifying that visually that the rocker arm geometry is good, our push rod length is adequate, and our piston to valve clearance is way more than we need to worry about. So not even worth putting an indicator on it, measuring it, because if it's over 100 thousandths, I don't even worry about it. But there are a lot of engines that it does get very close, and you know, there is a certain threshold to where it gets to the point where they're almost kissing each other. A lot of these higher horsepower setups, seen it, you know, high horsepower, big blocks, stuff like that. They'll get pretty freaking close for a very short amount of time. Basic rule of engines: no two things can be in the same place at the same time. So there you go. Let's bust these back off, put the actual valve springs on. We'll get rid of the test springs. Then we will be bolting the heads on. And I'm pretty happy with our one-piece guide plates. Usually I have a personal issue with these things because they never seem to really put the rocker arms where you want them. But in this particular case, they they're pretty close. So I think I'm just going to run them the way they are. A lot of times we'll cut them in half and kind of move them around individually and then weld them back together again. A lot of times you buy them as two-piece, and they kind of have like one kind of looks like a you know, like a tooth, and the other one looks like a groove, and you can kind of move them separately, and then once you get them where you want them, you tighten them down, and then you tack them in place with a welder. We don't really have to do that in this situation, so that's nice. Popping off the test springs, final 2 valve springs. Let me see if I can do this in a way that's still visible. So, retainer on the spring. We've already got spring seats installed, and the valve seals are holding everything in place, which is convenient. Spring compressor goes on like that. This is really just a glorified C-clamp, but it works just fine. Sometimes you got to fight with it a little bit, but anyway, crank that in. Whoops, I didn't mean to do that. Crank that in. Put our keepers in place. A lot of people like to put a little bit of grease on the end of the valve to kind of hold the keepers in place, which is a good idea. I typically don't do that because I usually don't absolutely need to, but can hold it in place, slowly release it. Got to make sure that those keepers are seated in the groove. Those are square groove keepers, obviously, because we got a square groove in the valve. But if radial groove, it doesn't matter. You got to make sure that those things are seated in the right spot, because if they aren't, and you release the spring pressure on there, you can break them. And a lot of times, see, that looks good. Nice and flush, everything's straight, retainer's straight, we're all good there. A lot of times, if you're getting kind of out of control there, the keeper's not really in the right spot, you might start to release the spring, unwind the tool, and retainer might kind of like snap into place. That's not good. Take it back apart again and look at those keepers, because a lot of times when that happens, you've cracked the keeper and didn't even know it, even though it snapped into place and is installed fine. I say that because it's happened to me, and I know people it's happened too. But yeah, they can crack, and then you take it apart, and then look at the keeper, and it's still in one piece, and then you flex on it a little bit, and it breaks right in half. Not good. There we go. Looks good there. Rest of these we did yesterday. These heads are now fully assembled and ready to bolt on. We are going to use just factory head bolts, because the power levels really don't require head studs. There's nothing wrong with running head studs. It's never a bad idea to do it, but I'm just going to run with these because I don't think the head studs are really necessary, to be honest. And these are just some Felpro 7733 head gaskets. No MLS gaskets here, because again, we just don't need them. They're expensive, and for the power levels and what we're going to be doing with this engine usage, it doesn't need an MLS gasket. So why spend the money if you don't need it, right? This being a factory GM block, we do have to put thread sealant on all the threads of all of the head bolts. Well, the reason why is every single one of these head bolt holes are drilled straight through the deck of the block, right into the water. So no, you don't put your regular CMD thread lube or your ARP bolt lube or anything on the threads. You got to use thread sealant, or else you're going to have water leaking up through the head gasket, up through the bolt, even up under the valve cover. It's just not good. So what I like to do, and it might be a little bit overkill, but I'll put the thread sealant on all the threads of all the head bolts, and then I'll even put some down in the holes just to make sure there's 100% something there sealing up, just to prevent any water leaks. Bit of unusualness if you're used to only building stuff with aftermarket blocks. Any aftermarket block, all the ones I've seen, I've never seen them where the head bolt holes are drilled through. They're always blind holes. So that's something you don't have to worry about. So you just run your regular bolt lube. But if you're running an aftermarket block, chances are you're running a head stud kit anyway. So, but anyway, a little bit of extra step there we got to take. It's a little bit different than we normally would do. All right, we're getting pretty close here with our above average Joe 383 small block Chevy. Carburetor's on, carb spacer's on. Actually had to have Brock help me out there a little bit. The square bore in the center was actually too small, and I don't know if it was just a defect in the manufacturing or what, but it's actually so small that it was interfering with the butterfly valves on the carburetor, so you couldn't even open the carburetor. So he green buttoned that, put it in the CNC machine and made it perfect and milled both sides, and that's all good. So avoided any problems there. Fuel pump, or mechanical fuel pump, is on, mounted. Made our fuel line here, fuel logs on, intake, water pump, all of our plugs, everything's all sealed up, pretty much ready to go. This here is a ready to run distributor that I got. It's not an MSD Pro billet, but it is basically a Chinese knockoff of one. I can't remember if this is a Summit deal or an All-Star, but regardless, it honestly looks like a carbon copy of the MSD Pro billet at about half the price. This thing's pretty freaking cheap. I mentioned it's ready to run. It's not. These are not ready to run. And I'm going to show you why they're not ready to run right now. So check this out. So this is an All-Star, quote unquote, ready to run distributor, just like the MSD Pro billet. However, it did not come with any kind of instructions. So I had to steal some from the MSD Holly website. I'm assuming this is all the same thing. If it's not, we're going to find out really quick once we get it running. But anyway, the reason why these are not ready to run is because the advance curve has not been set yet. Usually these things are shipped in the box with a really, really, really lazy curve where they have very, very little advance. If you were to just stab this in and run it as it is out of the box, you would have very, very little ignition timing at idle, and then it would just take a very long time for it to finally fully come to full advance mechanically. This is a mechanically advanced distributor, meaning there's little weights inside, and the faster the distributor spins, and the faster the engine spins, rather, the centrifugal force forces the weights to go outwards, and those weights actually clock the rotor and the distributor and advance the timing. I'm going to show you that right now. Pop the cap off. There's our rotor. See our contacts here. That's from the coil. This is rotates around the inside of the cap and the rotor. This contact here, as it rotates, makes contact with all of these points inside the cap, which is distributing spark out to all of 8 of your plug wires right from here. If I hold the distributor gear and keep it from moving, notice how I can turn the rotor and it kind of springs back. We are going to set how much that's allowed to move, which we're going to do with bushings. Going to also set how quickly it advances. So essentially, the faster the engine spins, the faster the distributor spins, and as it spins faster, the centrifugal force of the weights coming out will actually turn the rotor like this, advancing it. I want to do is limit how much it's going to advance it, therefore running more timing at idle. And I also want to limit the restraint on, I guess rather, the pressure on the little springs inside there to allow it to get into full advance quicker. So maybe these graphs will make it a little bit easier to understand. The bushings are going to govern how far the distributor is going to advance. And the springs that you use on the weights are what are going to govern how quickly it advances. How quickly meaning from idle to whatever RPM you want it to be in full advance at. If you've got like just a regular race car, a lot of times you just run a locked out ignition where if your engine's running happy clean at, let's say 32 degrees of total timing, NA, carbureted or whatever, you fire it up at idle, it's at 32 degrees immediately, and it just stays there. Since this is a street car, we don't need all that timing at idle, and we want it to drive nice and smooth, so we're going to have an advanced curve. So let's just say, for instance, at idle, it'll have, it could have 16 degrees of timing, and then by 3,000 RPM, I want it all in full advance at 32. Well, this is how you're going to do that. These graphs show you x-axis down here is RPM, and the y-axis here is degrees of advancement. Like I said, we got two variables here. We got the bushings and we've got the springs. So the advanced stop bushing, we're gonna tighten this up. So like I said, the tighter that this is, the more timing we can run at idle, which is what I want to do. So if we could run it like 18 at idle and 32 by 3,000 RPM, I'd be happy with that. So we just need to figure out the combination of the bushings and springs that are going to get the advance curve to that point. Well, we got to pop our rotor off first. And this can take a little bit of patience to do if you've never done it before. It can be kind of a pain, but it's not a big deal. It just always cracks me up to think companies ready to run distributors and they're really not. But anyway, here we go. Here's these weights I was talking about. So as engine speed increases, the centrifugal force on these weights forces them outwards. And it's probably hard to see, but as I pull out on the weights, it's actually mechanically forcing the top half of the distributor to rotate to the right, advancing it. Now, I can already tell just by looking at it, these springs they look pretty weak. So this thing's gonna have a really broad advance curve. The springs and the bushings, I mentioned both. These are the springs. Got our springs off. Take these little bushings off. Now, these are not the bushings that I was talking about. Those just kind of keep the springs in place. These are the weights. Those just slide right off. Now you're left with, this is your advanced mechanism here. It's as simple as that. What's keeping it from stopping back and forth? Well, there's these bushings I keep talking about, and you can see them from the underside here. See those little blue things under that nut? Oh, I suppose, yeah, there's only one. Right. So, you can see there, stops. So, essentially, what we're going to end up probably doing, I'm sure, is taking that nut off and replacing that bushing with a larger bushing. The larger bushing is going to take up more space in this open area here and restrict how much this can move back and forth, thus tightening up our advance curve. Again, that's only half of it. So we're going to tighten up the curve, but then we're going to adjust how quickly it advances with the springs. Now, in your ready-to-run distributor, you're going to notice there's a bag of parts. Kind of looks like this. Now, obviously, you got the top that holds all the plug wires onto the top of, onto the cap, rather. And, the gaskets and stuff like that. But, and the O-rings and all that good stuff, but you might think, what are these springs and bushings all about? Well, it's exactly what I've been talking about. I think we're likely going to end up with using the black here. It's been a while since I've done this, so we've got 2 heavy silver springs, 2 light silver springs, 2 blue springs, and we've got a red bushing, a silver bushing, a black bushing, and then a blue bushing that's, you already saw, is in distributor right now. Just got to bust this nylock nut off here, up under the bushing. There it is. Okay, there you go. There's our blue bushing. I want a tight, aggressive timing curve here, so we're going to run the black bushing. We know we're going to run the black bushing. Let's figure out what springs we want then. So these little graphs are pretty helpful, actually. But you can see right here, red, silver, green, blue, purple, black. Now this is MSD stuff, so they've got more bushing options than what we've got here, but this is talking about the color bushing that you would use. So as you can see, black in all scenarios, they're at the bottom, shortens up the timing curve, right? So as engine RPM increases, timing increases and then stops, right, with the black bushing. With this blue one, I don't really know. I can tell you right now that red one would be no fun. It'd just be advancing forever. We don't want that. So anyway, that's our black bushing. That's what all those different horizontal lines are meaning. Now this line here, the slope, is what we're going to change or adjust rather with our springs. We just got to figure out which combination of two we're going to use here. So let's see. This is one silver heavy, one silver light. So that would mean one of these and one of those. I kind of like that. I kind of like that one because timing here, that's our black bushing we're going to be using. And with those springs, we're going to be focused on x-axis here. So all in, with that spring combination, we should have full advance right around 3,000 RPM. If we did a heavy silver and a blue, that pushes us out a little bit more, maybe 3,250. Two silver heavies, that would bring us out almost 3,500. Kind of going the wrong direction there. Light silver, light blue. Yikes, we don't need to be in that soon. Definitely don't need to be in that soon either. So, and 2,500. Yeah, no, we're gonna do, this is the one. Black bushing, one heavy silver spring, one light silver spring. Heavy silver, light silver. That's our combination right there. Just do the opposite of what we just did. If you can't already tell, we've limited that travel quite a bit just now. Switching from that smaller blue bushing to the much bigger, fatter black bushing. Get our little nylock nut back on here. We don't want that falling out. I have some weirdo ignition timing out of nowhere. Okay. Slide the weights back on. And they just ride on here on these little pads. That's it. Gotta put these little bushings back on. One heavy. I'm gonna do this one first because it's gonna be a pain. Oh, don't be so dramatic. It's not that bad. I think I can do that one by hand. All right. One heavy, one light. You might be thinking, well, how is that going to work? The two springs are, this one's clearly way stronger than that one. Isn't it just going to hang it up? Well, no, because you got two weights and centrifugal force is going to pull out on both of them the same. So the combination of these two springs together with the same weight is going to give us that slope that we wanted there in that graph. So here we go. Put our cap back on. These usually only go on one way. Yep. I've dealt with a lot of pro billet distributors in the past. I've never actually dealt with one of these, but I have to be honest, I mean, for the price, it looks pretty much identical to a pro billet as far as the internals go. There we go. And then we can throw our cap back on. But we don't need to do that yet because we still got to install it. So there you go. Our ready to run distributor is now ready to run. All right, so time to stab the distributor in. And the way we're going to do this is get the number one piston on the compression stroke coming up towards TDC. Two ways really to do this. One, crank the engine over with your finger over the spark plug hole until you start feeling air come from number one. Or you watch the rocker arms. It's either going to be on the compression stroke or the exhaust stroke. So if the exhaust valve is closing as you're coming up on TDC, then you know that that's not the compression stroke, obviously, because the exhaust valve has been open as the piston's coming up, pushing the exhaust out. So don't want to do that. which you certainly could easily do, install the distributor that way. That's called installing it 180 out. And that's not good. That creates fire to the carburetor. So we're going to keep turning it. Intake valve is closing. Just closed. Both valves still closed. 50 degrees before. Hear that? I'm going to put it at like 20 degrees. Remember, we set that pointer. It's super accurate. So that would be top dead center, obviously. We're 20 degrees before on the compression stroke. Both valves are closed. And you heard air coming out of the spark plug hole here. So we're going to stop there. Back over to the rear of the engine here. Where the distributor goes, right through this hole back here in the back, just like every small block, big block Chevrolet, small block Mopar. Now there's a trick here, because you have your distributor gear, and then you've got the gear on the camshaft. Those two gears have to mesh together as the distributor slides down into place. Now, on top of all that, under the distributor, you'll notice that little flat spot. That is what engages the oil pump drive shaft that's sitting there down in the block right now waiting for us to engage. If we don't engage that drive shaft correctly, the camshaft will turn the distributor all day long, and as a matter of fact, it'll start, and we won't be turning the oil pump, and we will have absolutely no oil pressure. Not good. So it's kind of a little game where you stab it in there, you check it, pull it back out, turn it a little bit, turn the drive shaft, slide it back down, keep messing with it until you eventually get it to slide in. The objective here is to get the distributor set down in, engaged in the cam gear, the cam distributor gear, and engaged in the drive shaft with the rotor pointing at #1 piston. Just standard for small block Chevrolet, big block Chevrolet. That's just how you do it. So you can kind of cheat, and if I know I want the distributor to be, I want my electrical connections to be about here. Here's where the screws for the cap are going to be. I want the rotor to be sitting about like that. And if I turn it upside down, you can see that little tooth there is basically just going straight back and forth. It horizontally, like this way. So there it is. That's the oil pump drive shaft, and you see it's got the same kind of groove in it, and it looks like it's pretty close to being. Sorry, I'm having trouble with this light here. Pretty close to being where we want it. So I'm going to roll the distributor back, because it's going to turn as it engages the gear on the camshaft. It's going to turn the whole shaft in the distributor, while I'll be keeping the body right where it's at. So you'll see I'm holding the body still. You see how the rotor's starting to turn? That's it engaging the gear on the cam. We just got to find the oil pump drive shaft. There it is. Now, I think I'd like the rotor pointing a little bit further that way. No, you know what? Actually, no, that's gonna be fine right there. Because if I move another tooth, it's gonna be way out this way. So, yep, that's where we'll keep it. Now, the reason why I set the pointer at 20 degrees and not 0 degrees is because I'm factoring with the bushing and spring setup we just did in the distributor. We'll probably have about 18 degrees of initial timing, timing at idle. So if I install the distributor and set it up so that it's going to spark off at 20 degrees before top dead center, it should be pretty close. The engine will start with too much timing. It won't start with not enough. So if you're wondering about the 20 degree thing, that's why. And that's just me kind of estimating where it's going to want to be. Obviously, once it fires off for the first time, first thing we're going to do is get a timing light on the pointer and, just turn the distributor and get it where we want it. So, but yeah, so distributor's in now. Just got to make plug wires.
Okay, now you'll see that 10 weeks later, Joe has finally gotten this all together, because this is now turned into somewhat the most important engine and most dramatic engine that Joe has ever built in his entire life. Are you nervous? Because we've not started this yet at all. Stone cold on the dyno.
It's fine. It's going to be totally fine. As a matter of fact, I think it's going to fire right up as soon as that fuel pump primes.
Did you put the distributor in right?
I sure did.
All right, all right. Now we'll just give it a little squirt of gas. So we're gonna start this thing up, but I'm just letting you know that Joe happens to feel, and he might be right, that this is the best looking small block Chevrolet, old school hot rodder style, above average Joe style small block Chevrolet in the universe.
I'm biased to that opinion, but yeah, I truly believe that.
That it is the best.
It is the best.
The worst looking thing on this are my dyno headers. So we're going to dyno this thing. We're going to start up. What do you got on? Joe wants to do this with different rocker arm ratios, different carburetor, different what?
Yeah. So this would be the ultimate street carburetor, electric choke. We wired it open. Vacuum secondary, 770 CFM. So it should be very easily tunable and should run nice and smooth in a street car. We've got your fancy racy carburetor. That's a 750. I think would be kind of a fun comparison. Right now it has 1.5 ratio rocker arms, and we got a set of 1.6s. I thought maybe we could run 1.5s, all 1.5s, maybe put a 1.6 on just the exhaust. Try that. And then put a 1.6 on intake and exhaust. So it's a difference of like 50 thousandths of lift. Does it? I mean,
fair enough. We'll see if it does. We'll see if it does anything. That's fair. No, that's fine. That's fine.
At least we know.
So this is a good little build. So obviously, if you've hung on to this long, you're now through two buckets of popcorn. Your kids are going, I don't want to watch this anymore, and you're like, that's too freaking bad. You're gonna watch this until the end. That's what you're saying. And your wife, she left because you can't say that to her, because So
Why would she not want to see this?
I don't know why.
Every
Maybe
minute.
maybe your wife is the one that's saying, "You sit back down here, Mister, and watch this," because I don't want you to screw up your engine.
You don't want to miss a single minute of this.
You don't want to miss a single minute of this. So we're gonna have a bunch more time into doing this. So let's get at it. All right. First, we're gonna see if it's gonna just fire off like that. Is the ignition on?
I don't know.
All right.
Machine's right there.
So I didn't have the ignition actually on because I didn't know where which toggle switch Kyle wired up to. So I got that figured out now. We will now see it definitely got fuel. It just squirted in there. We're gonna see if it fires in the hole.
Yes.
Purrs like a kitten.
Is that oil pressure?
No.
I
Yes,
saw
it
it.
Now, Joe's setting timing. Don't let Joe's expression fool you. Because I saw him when it fired up, and Nate didn't have the camera on him. It was like, he has been working on this 481X right here. Assembling that today. He just got done assembling Travis Meehan's. So that makes like pretty close to 4,000 horsepower, right? This is the most excited
I've seen it.
feeling that Joe is in a long time. Right now, he's like a 12-year-old kid that's getting ready to go to the monster truck race. He's going to get to go and sit in the monster truck or something. Joe actually probably wants to stay in there during the dyno.
He'll run the throttle.
Oh, look at that.
Snappy.
Chris. All right. Hole number one.
Boy.
Might be pretty good. All right, so that's hole number one with Joe timing, Joe jetting. Ooh, Joe jet.
Joe jet?
Joe jetting.
Happy to know.
You shouldn't have a fan.
Oh, you got a little oil, or you got your
What are
dipstick tube over here. It's oh, you know what's doing is that freaking. You know what's exactly smoking over there?
Yeah, the breather that
The
would have
breather I told you
it would have dumped all over the
It's
engine.
It's just sitting there burning on. All right, let's take a look at this. That just went up to 5,000 RPM.
Off the charts and the
It's
wrong
off
way.
the chart the wrong way. Alrighty. There we go. That looks more reasonable-ish, doesn't it? There we go. All right. So we are at 482 foot-pounds of torque, 421 horsepower. I think everything's all looking pretty good. That looks fine.
Yeah, a little bit better than you thought it was going to be.
Everybody's down you, Joe.
Did it?
We haven't even put the 1.6 rocker.
I don't think anybody had it nailed for 500 horsepower. But I don't think it's gonna make 500, but we'll see.
That's a nice torque curve.
That is good torque. That is good torque.
Make a really fun street car.
All right, let's hit this thing again. Harder. Gotta stop. Gotta stop. Because your freaking nails hurt. Ah! This is what we do all day. We dog wrestle. Dog wrestle. Dog wrestle. Got him in a headlock. Get him in a headlock. Yeah, get him in a headlock. It's a fighter. It's a fight dog.
Lights right up, man.
The pure excitement of under 500 horsepower is exhilarating.
The most undramatic engines I think this dyno's maybe ever seen.
No. We just had one on here.
Yeah.
Yeah, the Hamburglar there, Rick Nonsense. All right, ready? You got a, is there a rev chip in that MSD box?
I don't know.
Sounds like there's a 6,000 chip in that box. All right, so we're at 439, 488. Looks like it's laying over up there.
Top one, yep.
Looks like it's laying over up there. Yeah, it does. That's duplicated nicely, so that's no problem. That's the first hit. Let's get to this one. There we go. Well, I mean, it makes peak out here at 4, so it should make peak around here at around 55, 56. So I'm not expecting it to go too much further out here. Well, double AJ.
It lays over pretty quick there at the end.
That's just me letting off the throttle.
Oh. Well, we should probably.
Just a FYI, it doesn't hit like 60 or 5,900 and then go down to.
I know that, but
It is laying over up here, but I could hear it laying over.
yeah. Well, we should probably make sure it doesn't have a rev limit in it.
Yeah, it sounds like hit the rev limiter.
Yeah.
See if there's a chip or a setting on that. I'm not sure which one that is.
Go in there and change the dials.
Kyle.
You should have been like 7,500.
It ain't gonna make no power at 7,500. It ain't gonna even rev.
Don't be scared. I have this amazing sense of like no offense, but no concern. It's like
Well, there's no customer to worry about.
yeah, it's no customer to worry about. It's Joe's.
If it
It's your
scatters,
freaking
it's
engine.
my freaking fault. Yeah.
I know. I really want to run it with no headers.
Yeah.
See what it does.
It's gonna f up the paint, is what it's gonna do.
It's not what paint. It's just gonna blow. It's just gonna blow the flames out directly.
Towards the
in
fuel
side.
tank.
That is
We'll move
true.
the fuel tank till we do it. But anyways, why don't you go in there, check it out, and see, make sure everything's all good in the hood. I mean, that's two hits. So, and we got to turn up that rev limiter. Just turn it up like 7,
Because we're not gonna
8,
We're not gonna go there.
8, 85. I don't know. It's probably go 9.
Why not 10?
They build 10,000 RPM small blocks all the time.
Yeah.
Every
It's like-
single 327 small block
Ev-
that existed in history is revved at 10,000 according to everybody on.
Kyle's
Yeah.
great grandpa in 1932 had a Ford flathead that ran 10,000 RPM. This is on the wrong tachometer setting. It was on
Also, is that
4 cylinders, but just kidding. His great grandpa didn't ever have such a thing.
It was
Hey.
9,000 RPM.
It was 9,000, not 10. Don't be stupid. Okay, you're gonna check that thing out.
Yep.
And then we're gonna come back when Joe gets done doing his inspection. Did you wipe
Yeah.
that off?
No. So it's another thing I'm wondering is if the plug's just too cold.
No, don't worry about that.
Okay.
The too cold plug is only really shows its face at idle and stuff like that. It doesn't really care if I open throttle. At least in my opinion. We'll run the coldest freaking plug you can possibly imagine in the wagon.
Mm-hmm.
This is a nitromethane plug. It would run that same plug, you know. So, but yes, gonna add some timing to it, which will clean up the fuel because it looks like it's still got some fuel in it. So that's good. This is just tuning old school way because just not retooling up everything. Not right now. So, yeah, let's throw some time in it, making our hit.
Maybe 2 more degrees.
Yeah, 2 or 3 at least. That'll probably get up there, and then I think you can do your. Then it'll be pretty close. I mean, we can flog on it all freaking day long, trying to make it perfect, but it's gonna run pretty good. I think we might as well go after the rock arms if you want.
Yeah.
Yeah. Yeah.
I do. Let's do it.
All right.
All right. Let's
3 degrees.
throw timing in it.
Settle down.
Okay, Joe.
Hold it. Forgot to change the rev limiter. He forgot to change the limiter. So let's see what it looks like compared to. This would be the same pull with 3 degrees more timing. Now this is actually believable that it would lose a little bit of torque. So, it's lost 14 foot-pounds of torque with timing. And then up here, it's actually, the same, but fell off here. But it's a little hard to say when it's hitting rev limiter up there. The torque is believable. I got a question for all of you guys out there. Why would it take less timing at peak torque than peak RPM? Like peak torque versus peak horsepower. Or does it? Or does it not? Good question. None. Did you change it?
Yeah, it's at 7,500 now.
Oh, all right.
Should get near it.
Get near it. All right, let's see what we got here. There we go. I picked up again.
Sounded better in the big end.
It sounded better, yeah. All right, let's see what that looks like.
After that.
See, yeah. So it carried out. It probably was tickling that rev limiter out here is why it does that. So let's see here. That color is terrible to see. Let's go with lime green. There. Actually, yeah, no, that is just flat out. Yep, that it picked up maybe this 1 or 2 now. Now I don't know why it all of a sudden picked that up. Didn't change anything.
Picked up torque too.
Yeah, it picked the torque back up. So I don't know. Huh. All right. Well, I don't think that's that bad. You know what? I would go in there and let's put in like 2 more degrees of timing. Just see what it does. See what it does. See if we can still get it to carry out a little more out there. Kale?
Yeah. Do it.
Double A Joe has put, how much more time did you put in it? Another 2?
2 more degrees.
Another 2 more degrees. What's that give it?
38.
38. Yeah. That 38 total. It's not abnormal. It's not boosted.
Seems like a lot. But
Huh?
Seems like a lot, but
Nah, it's all right.
well, we'll see if it likes it.
We'll see if it likes it. Sounds like a freaking top fuel car, Joe.
Oh yeah. Oh, I actually liked it.
Yeah. Well, that's a pretty minimal gain, but yeah, it did. Let's see what it did.
Definitely picked up torque.
Yeah. Let's see, and it is smoothing it out and just making it better. It probably is
Oh, the black line for torque is nice.
the black line for torque. That's logical. Okay. There you go. Alrighty. So I would say 450, 497. It's mainly, but it really did really well out there. So we could put, you could put 2 more degrees of timing in it, and it's still not hurting. It's not hurting torque any. I'm totally backpedaling. The question is still valid. Why you would have a timing curve? It just happened to prove out differently. Well, it hasn't proved out differently. It still will be the same. So just give me the reason of why it would need. Don't answer it if you know. You should know of why it would need more timing at peak horsepower than it would at peak torque.
I'm not saying anything.
Huh? All right. So, anyways, it's still correct. But here we probably just haven't found the magic spot where it wants to be at. But we're probably in the grand scheme of life. I mean, we're now going to be making 1 or 2 more horsepower every time, which is not really a big deal.
Right.
And you're hard pressed to send an engine out that has 40 degrees of timing in it, or
Right.
42 degrees of timing in it, and not have somebody take the timing out anyways. So
Yeah.
so I think you should just leave it there. I mean, even I have a mental block at over 40.
I
But
think,
anything over 40 is like, nah, I just can't do it. I can't do it.
yeah,
I just can't make it happen. So I say we just leave it there.
I'm totally fine with that.
All right.
I
so
don't
let's
care
leave
if it picks up 2 or 3 horsepower. I'm not.
Yeah.
That's not worth 2 degrees.
Yeah. So now we have. Oh, this is our horsepower guess list. Now we haven't finalized everything yet, but currently Joe is in the lead with exactly 450. But we're
Decent
trying.
guess.
But we're trying a decent guess. But we're trying to make more. Kyle was underly optimistic at 434. Cody 433. Brock 483. Nate 467. My wife comes in at 492. So if somehow, some way, my wife ends up winning this thing,
I'll be super excited. But
you'd be super excited. Yeah.
I don't think we're gonna pick up 50.
She'd be super excited.
I don't
If she
think
knows what she's gonna win, if she does, she'd be super excited.
we might have to hit it with a little bit of nitrous or something to get there.
Yeah. And then I was at 484, not knowing nobody knew what somebody else guessed. So this is all flat out top secret guess. Bert, Joe Burt, who's walking around working on my car, doing something. Not sure where he's at right now. 441. Reed, new kid Reed at 465, and Real Deal Neil at 464. I don't know how they got one apart from each other either, and they're probably going to be the closest to it.
Yeah, probably.
Could be.
That's not fair.
That's yeah.
I don't think we're gonna pick up 50 horsepower with the 1.6 rocker on.
No, probably not. But you never know. It might be hurting for camshaft.
Yeah.
Do it to it. Which way you're going to go first?
Well, does it make sense to just try to throw a 1.6 on the exhaust,
Yeah, that's what I would try at first.
and then we'll just do both, which is where we're
Yeah.
gonna end up. So we got 1.5 rocker ratios, intake and exhaust, and we're gonna take off the exhaust and we're gonna put 1.6s on the exhaust.
Yes.
So we'll have
Effectively
1.5
making it-
intake, 1.6 exhaust.
effectively making it a bigger exhaust lobe.
Yeah.
All right, let's try that. 1.6 exhaust rocker. It's on. No other change in tune-up, just a rocker arm. Let's see what it does.
Al didn't seem to care at all.
All right. So the logical thing to do here is put the intake rockers on it. We'll run it. Then we'll take the exhaust rockers back off, so therefore it would only have 1.6 intakes.
Okay.
All right?
Yeah.
So we got 2 more pulls. See what it'll do.
Good.
Engage. Wow.
10 horse.
Wow. It wants some intake rocker on it. How about that? All right.
That really cleaned. It at least sounded a lot cleaner.
Oh my gosh, it made power at 6,000
Yeah,
instead of 5,300.
and sounded a lot smoother on the big end.
Yeah, that's actually probably me just pulling back on throttle a little bit early right here. But yeah, that's interesting. All right, get them freaking junk 1.6s off the exhaust and let's see what it does.
Yeah,
I'm totally surprised. I am honestly, it's backwards from what I thought it would be.
yeah.
But that's cool.
Well, there you go.
If you were really hardcore, you would have had 1.7 rockers for it.
Well, then I probably have to get like Jessel deal, and that's not so average, Joe.
Yeah, that's not so. That's triple A's. Above average, Joe.
What I should have done is just got a camshaft ground for it and just had it made the way I wanted.
We should have just got it. Yeah, we could easily design a camshaft instead of just getting something off the shelf, but that's all right.
Yeah.
All right. Yeah, let's get the rocker arms off it. That's interesting.
Yeah.
That's interesting. All right, one last time. Do you think that it's funny that Joe videos his engine while we're standing here videoing the exact same thing that he's videoing?
Yeah.
He's gonna use it for his own personal collection of videos.
Yeah.
All right.
So
All right,
I got it right away.
Is it gonna be better? Is it gonna be better with just 1.6 intakes and 1.5 exhaust?
Well, putting the 1.6s on the exhaust, it didn't seem to care at all. As a matter of fact, hurt it a little bit. The 1.6 on the intake, it really liked that. So I'm gonna think I would be really surprised if it actually did better.
I officially am gonna say I do not know. I do not know. This is why we test stuff to figure it out. I don't know. I was surprised the first time, so we'll see. Let's do it.
Yeah.
All right.
Water on?
Nope. Thank you.
Thanks. Ow. I think it actually liked that.
I think it didn't hurt it.
I'd like to point out that I'm now 1 horsepower away with my guy.
Oh man. Yeah, but Neil is 464. What'd you guess, Nate?
467.
465.
It's 465.9. Oh, you're gonna split. If we split hairs, I think
Reed's winning right now
Reed's winning.
by point.
Oh crap!
0.09.
Reed's winning.
Yeah, Reed's got 465.
I don't know how they came up with their two guesses because
that's BS.
Reed doesn't hardly know anything yet. What the heck? Reed, oh, now that little hump deal came back pretty hard.
Yeah.
Hump, he came back hard. Well, because we're in our light blue line, so same. Slightly better, slightly better. Slightly better. You know what I want to do? It's all warmed up right now. It's not a direct fair comparison, but I think that it tells us what it did do. I mean, it made 465. Let's do another run right now. It's got its crap all together. It's going, oh wait, I have a 1.6 rocker arm on the intake now. So wait, I didn't have it all wrapped around.
I wasn't ready.
That wasn't ready. Now it's ready. Let's see if it smooths out or if it's anything different. All right, let's do it.
Hope those secondaries are open all the way.
Well, I'm sure they are. That's too good a horsepower to not. Yeah. Yeah, that's too good a horsepower to not do well. So. All right, let's do it. Now it's ready.
It sounds better.
Yeah, it's happier. It's adjusting. It's like settling in. That's very possible. Wow. A little bit down. All right. But it made a little more torque. That won't back down at 5,300 again.
Yeah, it's good.
No, now it's did smooth itself out some. Made a little peak there, a little bit low there, and just didn't run up hard on it. Ah man, I think it needs 1.6.
Yeah.
Oh, what was our yeah? It needs 1.6. I think is the best,
That would make the most sense.
and it makes the most sense.
It's just interesting. I really like that extra on the intake.
Yeah, that was 1.6 exhaust, 1.5 intake. This is 1.6 intake, 1.5 exhaust.
Yeah.
Yeah.
All right, so let's switch out the exhaust one more time, run it one more time, and then we're done.
Oh my gosh. All right, hurry up.
So just put,
All right. Alrighty, so Joe wanted to back the thing, so we got the rocker arms on there. So 1.6 just to re-verify where it's at. Then we're gonna throw this carburetor on. I have no history on it at all, but it's a Pro Systems 750 annular booster carb. With no choker, yeah, it's a full race version. So we'll see what that does. Then we might decide if we're going to tune on the carburetor, but we'll run it as is first. I think that's actually pretty consistent.
Yeah.
All things considered, that's pretty much the same.
Yeah.
I think that's pretty much the same. All right, carburetor time. One used shop carbonator. Alrighty, new carburetor on. Let's do this thing. Got to fill the fuel full of carburetor, or fill the carb full of fuel. That would make more sense. Oh, idle's a little high. That's all right. Hey,
More. With a proper carburetor on it.
a proper carbonator on it. All right, so that is totally untuned. Let's take a look at it. Yeah. And we could probably obviously make this better. There you go. Same. And it picked up here where you'd figure it would pick up. I think it could be better with that. I would expect to have probably, I'd say at least 484.
Yeah, when that carburetor's
Is that your first guess?
What? Oh my gosh. That was my guess. That would be so amazing.
That would be nice.
All right, everybody. We're out. What are you going to do with this engine anyways?
I don't know yet. I got an engine, but no home for it.
Well, that's like a lot of customers actually we have, so I don't know. I don't know.
It was really just something to do for fun, like I explained, and this has actually been a lot of fun. Now
Yeah.
I've got a really nice, pretty engine, and I don't have anything to do with it. Now the fun's over.
Yeah. Well, all right, we're gonna end this video because it's long, and I hope you guys have eaten all your popcorn, you enjoyed everything on this whole deal. Let us know if you like this kind of content. We're gonna do maybe like these long form videos like on a Saturday, so you can watch them over the weekend or something. Let me know if that's something you're interested in. Got any questions, any comments? Feel free to leave it. I'm Steve Morris. That's Double A Joe, and the Double A Joe engine. Oh, you still left that rag in there. Oh, okay.
I slipped it back in because
It's still leaking. All right, cool. We're out. Have a great night.